Welcome to the Nucleophilic Substitution reaction simulation. Here you will learn about the two main types of substitution reactions and the factors that promote them. By the end of the simulation, you will be able to confidently predict which type of substitution is most likely to happen. I don't know about you, but I could do with some refreshment before we get started on the chemistry. We should go check in on our friend Corey at the cafe. He could use our help brewing up some fresh flavor ideas. Click continue to start your mission. This simulation uses voiceovers. Using the lab pad is an important way to get the most out of the simulation. Is this the first time you've played a Labster simulation? Perfect. Then let's get started with your first mission.
So glad you could make it. I'm in a bit of a quandary with your amazing chemistry skills right about now. This isn't exactly moving at the moment. I really need to come up with some crafty brews to bring in a cool crowd. I was hoping to attract more customers by adding new flavors to our brews, but our delivery got delayed and I'm going to be short of stock tonight. I could really use your help. Do you put some flavors together in the lab? Check out the guest flavors we had planned.
Click on the different drink tabs to learn more. Click on the lab pad for more information.
You seem pretty chilled about this gastronomic challenge. Would you be up for synthesizing some flavors in the brew lab? An absolute lifesaver. My lab skills really suck.
Click on the neon beer signs to teleport back to the brew lab. Pick up a lab coat from the rack. Pick up the safety goggles. Find a glove box and click on it to put on a pair of gloves. Okay, we're all fitted out now to get involved in some flavor chemistry. Head to the hollow table to see what type of reaction we can use to make our flavor molecules. Go to the hollow table. On the hollow table, you'll see the product of a classic chemical reaction. Let's rewind the reaction to discover the starting materials and get some clues about the type of reaction we'll be working with. Press the arrow on the hollow table screen. Let's watch the reaction in reverse, from product to reactants. A trigonal bipyramidal transition state is formed as the bromine and hydroxy group coordinate to the same carbon. Press the arrow again to complete the reaction. As we rewind from the transition state to the reactants, notice that the starting components are an alkyl bromide and a hydroxy nucleophile. Let's explore the reactive components of the starting materials. Identify the reactive centers by placing the reactive center clouds. Which type of reaction have you just seen? Feel free to lower the lab pad and replay the reaction using the forward and backward arrows. That's right. Substitution is effectively substituting one functional group for another. Good work. The substitution reaction is a versatile tool we can use to design our flavor molecule syntheses. You spotted that we need a good nucleophile and an electrophilic substrate with a good leaving group attached. This particular flavor of substitution reaction is known as an SN2 reaction, easy to remember as S stands for substitution, N for nucleophilic, and the two lets us know that two reagents are involved in the rate-limiting step. Depending on the products we wish to make, we need to select appropriate combos of nucleophiles and alkyl halides for each of our substitution reactions. So first off, let's take a look at some potential nucleophile candidates. Go to the main wall display. You'll have noticed in the hollow table reaction that the nucleophile unit dictates the functional group installed in the substitution product. On the table, you have 5 different nucleophiles to choose from to synthesize each of the brew flavor molecules on the wall. Check out the functional group poster here in the lab if you need a refresher on those. Pick a nucleophile to make each flavor product. Fantastic work. You really know your nucleophiles. Awesome work. Chemistry is really just a big game of molecular mix and match. Substitution reactions are one of the most flexible syntheses used to define organic compounds. Careful matching of a suitable nucleophile and an alkyl halide starting material, we can create an assortment of tasty flavor molecules. Now that we've identified the nucleophiles, we need to make each flavor molecule. Match each one with the corresponding bromide starting materials. Select an appropriate alkyl bromide for each synthesis. Click on the lab pad for more information. One or more of your alkyl bromide selections are incorrect. Incorrect answers are indicated by a cross. Please return any incorrect bromide cards to the table and try again. You're a bromide detective. Once we know which flavor molecules we want to make, it's easy to work back from the target product to design a synthesis. You might hear of this referred to as retrosynthesis, with the retro simply meaning backward. Before we look at designing reaction conditions, there's one more structural detail we need to consider with our alkyl bromide substrate. Select an appropriate type of bromide from the drop-down menu. You're on the ball with your alkyl bromide knowledge. Good work. Since substitution really is essentially substituting one functional group for another, it's easy to work our way back to the starting materials we need to make our group flavors. Which alkyl halide makes the best starting material for a substitution reaction? Alright, you got this. When it comes to leaving groups, iodide is king. As the size of the halide increases, the CX bond weakens, making iodide the best leaving group and the best starting material for an SN2 reaction. Alkyl bromides are almost as good. At the other end of the trend, fluoride is such a poor leaving group that we rarely see SN2 reactions with fluoroalkenes. Brilliant work. You really got the alkyl halides sussed. Alkyl bromides serve as excellent starting materials for substitution reactions, given how readily bromine acts as a leaving group. The type of bromide you select, either primary, secondary, tertiary, or benzoate, can have an effect on reaction rate. Before we get stuck into making our flavor molecules, let's explore some other factors we might need to consider in designing our substitution reactions. For an SN2 reaction, what makes the best nucleophile? Brilliant work. SN2 reactions work best with a strong nucleophile. A highly charged nucleophile or base works best. But be sure to pick a slimline nucleophile. Steric bulk is the enemy of SN2 reactions. Neutral or bulky nucleophiles make for weaker nucleophiles, and carry out substitutions in a different way, but more on that later. Select the reaction pathway that uses the best nucleophile. You've got it. The best nucleophiles are high energy, so you correctly picked the curve that started highest at the reactant end of the reaction energy diagram. The higher the energy of a nucleophile, the easier it is to overcome the activation energy barrier and begin the reaction. How many steps are there in an SN2 reaction? Hint: Take a closer view. Got it. An easy way to remember this is that although the 2 in SN2 refers to the number of reactants, they react together in one reaction step. Energy diagram of this concerted reaction uses the reactants form a high-energy, unstable transition state. The selection of a good nucleophile is essential to the success of the SN2 reaction. As a one-step, concerted mechanism, highly charged, high-energy nucleophiles are required to overcome the activation energy required to get the reaction going. But it's not just how good a nucleophile is, the solvent that surrounds it can also play a part. To understand how solvent choice can affect the course of our reaction, we must first refresh our memories on the different classes of solvent. Go to the fuel hood. Group the solvents into classes by placing them on the appropriate shelf. Got all the solutions. Substitution reactions, or any reactions that have charged reactive species, are particularly sensitive to solvent choice. The nature of some solvent types means our nucleophile can encounter additional bonding interactions that hinder reactions. Let's consider the role of solvents in substitution. Protic solvents that contain OH, NH, or labile protons can form hydrogen bonds with charged reactive species. This means protic solvents can cage nucleophiles and prevent reaction. Aprotic solvents, those without any labile protons, leave nucleophiles free to react easily with the alkyl halides. Why do you think polar aprotic solvents increase the rate of an SN2 reaction? You're spot on. The inability of aprotic solvents to hydrogen bond or solvate with charged reactive species leaves nucleophiles free to attack the alkyl halides. Go to the wall display. Pick the reaction pathway typical of a solvated nucleophile. Absolutely. Solvated nucleophiles are less reactive due to solvent cages, preventing them from reacting with the halide. Molecules or ions that are surrounded by protic solvent molecules are said to be solvated. The solvent forms a shell around the nucleophile, and this reduces the nucleophile's ability to attract an electrophile. Choose the curve for the reaction with the best leading group. Nailed it. The best leading groups reduce the activation energy required to kickstart the reaction. Go to the hollow table. Steric hindrance is another factor that can affect the SN2 reaction. Check out the alkyl bromide compound on the hollow table. Switch between molecules to increase steric bulk on the carbon 1 or bromo position. Switch between molecules on the hollow table by using the arrow on the hollow table screen. As we replace hydrogens on the C1 position with methyl groups, the steric bulk around that atom increases. Switch between molecules on the hollow table by using now having replaced both small hydrogens with bulkier methyl groups. There's less space for a nucleophile to attack the carbon. Feel free to switch between the molecules to see the steric bulk increasing. See for yourself how larger functional groups can get in the way of a nucleophile approaching, making it energetically more difficult to initiate SN2 reactions with bulkier alkyl bromides as starting materials. Go to the wall display. Pick the curve for the reaction with the bulkiest halide substrate. That's right. Bulkier substrates block nucleophile access and need more activation energy pumped in to proceed. Now you've explored the various factors affecting SN2 reactions, you can check the Media tab in your lab path for a summary of the reaction energy diagram discoveries. To have the best chance of substituting a bulkier halide in an SN2 reaction, got the hang of this. Secondary halides can be sluggish to react in an SN2 reaction, and tertiary halides may not react at all. However, it may be possible to promote an SN2 reaction by optimizing the other reaction conditions. Go to the workbench on the left. Make a hypothesis about the order of alkyl bromide reactivity. How does your reactivity prediction look for these conditions? You can find confirmation in the graph. It reveals bromide substrate consumption over time. Return to the Hypothesis tab to check if your hypothesis was correct for this reaction. Be sure to make hypotheses for the substitution conditions on both screens. We'll be having an alkyl halide reactivity pop quiz soon. How does your hypothesis check out? The graph reveals bromide consumption over time, so which bromides are the most reactive under these conditions? The Hypothesis tab to check your predictions here. For alkyl bromide reactive, make sure Interesting. We see a complete reversal of alkyl halide reactivity between the two substitution reactions. 12 in one substitution reaction release the chemically hindered bromide as the most reactive. In the other, under different reaction conditions, we find that tertiary bromides are the most reactive. How can this be? In the iodide substitution in acetyl, primary alkyl halides react the fastest. However, tertiary bromides react most rapidly in the substitution which uses water and a nitrate nucleophile. Choose a statement that explains this reactivity flip. You're all over this. You're right, there are competing mechanisms at play. Go to the hollow table. As you might have guessed from the opposite orders of reactivity in the two substitutions we compared, a second type of substitution reaction can occur, the SN1 reaction. Let's check it out at the hollow table. Press the arrow on the hollow table. The first step in an SN1 reaction is the formation of a carbocation. Identify the reactive centers. The hydroxide nucleophile can attack the planar carbocation from either side. Here we see inversion of stereochemistry in the product, but the nucleophile could just as easily have approached from the other side. This is why we see a mixture of products in SN1 reactions. If your substitution gives you only one product with inverted stereochemistry, your reaction probably went via a concerted SN2 reaction. Since SN1 reactions involve the initial formation of a charged reactive intermediate, weaker nucleophiles and charged solvents can promote an SN1 mechanism over SN2. And if you're dealing with a bulky substrate, well, you're more likely to see slow carbocation formation than getting your nucleophile anywhere close. We can also optimize reaction conditions to encourage one type of substitution over the other. However, even optimizing all the variable factors can't force a bulky substrate or poor nucleophile to react. Let's take a look at one last energy diagram to compare the SN1 reaction to SN2. Go to the wall display. Select the SN1 reaction pathway most likely to proceed. That's right. SN1 reactions proceed via the lowest energy transition states. In chemistry, the reaction that has the lowest activation energy to overcome is the one that's most likely to proceed. As the SN1 reaction is a two-step reaction, we see two peaks in the reaction energy diagram. The first being the slower, rate-limiting step, carbocation formation. This is one of the clues we can look for when trying to work out whether something reacted via an SN2 or SN1 pathway. Now it's time to put our substitution smarts to the test. Let's get some practice in prediction. SN1 versus SN2. It's time to select the best solvent for each of your flavor syntheses. Go to the fume hood. Match an appropriate solvent to each reaction flask. Nice one. You selected appropriate solvents for all 5 reactions. As you worked out, the reactions likely to undergo SN2 needed an product solvent to allow speedy nucleophile work in this one-step reaction. You also worked out that those reactions either with bulkier bromides or weaker nucleophiles might proceed via an SN1 reaction, and that protic, carbocation stabilizing solvents would be a match made in heaven. Which solvent would best favor an SN1 reaction mechanism? That's right. Polar protic solvents stabilize the resultant charged carbocation that results from the loss of a leading group. Polar protic solvents can sometimes act as nucleophiles in SN1 reactions as well as a solvent. Amazing work. I'll bet you found one of those solvents trickier to select than others. Under optimal conditions, primary halides usually favor SN2, and tertiary halides tend to go for carbocation forming SN1. However, secondary halides can be harder to predict. Many secondary halides will go either way. If you have a good nucleophile, you could encourage either an SN2 or an SN1 mechanism simply by choosing a solvent that will favor the pathway you want. Corey will be delighted. You've applied all you know about substitution to design and synthesize all 5 flavor compounds. Let's head back to the cafe to see how your flavors went down.
What a crazy night. People went wild for the flavor drinks to compare. We completely sold out. I really hope you won. As you can see, I have a bit of clearing up to do. Then I have one last challenge for you. Some folks said their lavender lemonade tasted like coriander. Can you investigate how this could have happened?
Find and compare the lavender and cilantro flavored drinks. Examine the flavor molecules and see if you can work out where we went wrong. Investigate the empty drinks to find the molecular source of the cilantro problem. Raise your lab pad when you're done. Did you manage to figure it out? Great. You are a real lab genius. Why does the lavender lemonade taste like cilantro? You've got a keen eye for chemistry conundrums. The lavender flavor compound is R-linalool, but its stereoisomer S-linalool is responsible for the flavor of cilantro. Changing one stereocenter makes all the difference between a herby-tasting brew and one with a floral flavor. Inverting even one stereocenter changes the chemical and physical properties of the molecule.
Thanks for checking that out. New cilantro and lavender should be similar in some ways. I'll be sure not to mix up the isomers from now on. Cilantro is a bit controversial. Thanks for your help making these amazing new brews. Have one on the house.
Let me ask you one last question. Do you feel like you gained relevant knowledge during this simulation? Thank you for your feedback. Your score has been saved together with your 100% progress. Congratulations, you have completed the simulation. We hope you enjoyed it and you feel wiser now.